The seniors' last day, just in case you wanted to know, is going to be the 12th of May. Your last day of classes is going to be Thursday, May 21st. Thursday, May 21st. So that is 5 more weeks. 10 more days by my math. Look at that. Then Friday, the 22nd, is like your first day of summer, as far as I'm concerned. That seemed like what it sounded like. You guys are not going to have finals. There are not going to be finals. Wow, I really like the reaction. I saw Miles and Kobe's reactions there. I don't know if I didn't see anyone else's. Those were pretty good. So there's no finals. Instead, your second semester grade will be determined half from quarter 3, half from quarter 4 grade. Our grades are looking good in here overall for quarter 4. I'm not trying to like hurt anyone's grade. Okay, so I'm trying to help it for quarter 4. So that is how your second semester grade is going to be determined. Just so you guys know, it's not an issue in this class at all, but letters of concern are going to be going out via email to you and your parents, if you're getting any, on Wednesday. So I would just make sure that today and tomorrow, probably today, you look at Blackbaud, make sure you have any missing work in, ask the teachers during office hours today at 2 o'clock if you have questions, if you want to avoid any letters of concern going out. Again, I'm not personally sending any in this class. Our grades are good, but I don't know about your other classes. So just be aware that will be due for teachers by Wednesday to send out. They might even send them out earlier. So talk to your teachers today if you have a question. And then if anyone's in danger of failing for the year, I hope none of you are in any of your classes, but if you are, that information for teachers is due to Mrs. Metcalf by the end of the week. So just be aware of your grades. There's going to be some parent communication from teachers this week if your grades are not looking good. So just be aware of that. I think that's, also, this is going to be my last week. Okay, so Wednesday will be my last day of teaching you guys. Friday is going to be my last day. So I'll still have office hours up through Thursday. Mr. Bombalski is going to be taking over your Zoom classes for the rest of the year. Give pumps. There wasn't the same pump up as the no finals, which is probably better news. But I sent him a bunch of stuff that I prepared for calculus prep. Sent some final review, which is unnecessary at this point, so that's cool. And then whatever he wants to include at the end of the year. So our goal for the rest of the year is just to prepare you guys for Calc, basically. So that's what he's going to continue doing for you guys. But if you have anything missing up until this point, I recommend that you get it into me by this week, because he doesn't have all the same info that I have for this quarter. So if you have anything that you want to turn in, get it to me by Thursday, please. Questions? Questions? Okay. All right. Today, we are going to do another calculus prep lesson called the definition of the derivative. So let's bring that whiteboard up here. All right, and I'm going to end class a little bit early today because I have a virtual doctor's appointment. That's pretty cool, right? Okay, so this is going to be the next calc prep. Definition of the derivative. What's a derivative? You're about to find out. So limits, we already covered. That'll be covered more in depth next year, but limits are a big part of the initial phase of calculus. And then limits are actually used to define a derivative, which is like the second main thing in calculus. The last one is the integral. And everything in calc is one of those three things. So this is the second main idea of calculus. We're going to do a little PC, pre-calculus, before delving into the calc part right now. So I will do pre-calc work in blue here. Now, when I say pre-calc, I don't just mean stuff that you've covered this year. I literally mean stuff that is happening before calculus to get you set up for calculus. A lot of that stuff is just basic algebra. So I'm going to do what might seem like a very simple review, but unless you have it down pat, it's not helpful. So let's just get into some pre-calc stuff. Again, this is mainly like algebra 2 kind of. Okay, so let's let f of x equal 3x minus 7. That's a function, right? It's a linear, make a line. And its slope is 3. Its y-intercept is -7, right? So what you should know by looking at this for calc is that this is a line. It's linear. You need to know what it looks like. We can do a couple things with this line, right? We can plug in certain things, right? If I asked you to evaluate f of -2, you could do that. You would just plug in -2 for x. So we'd have 3 times -2 and then -7 more. So we'd have -6 minus 7, which is -13. So that's evaluating a function at a point. That means that the coordinate point when x is -2, its output y is -13. The coordinate point -2, -13 is on that line. You could do that for any number because this line exists everywhere. There's no holes, jumps, gaps, just a line. Now, we can get into something that's a little bit more abstract, right? We can plug in a different variable. So let's say we wanted to find f of a. What does that mean? Well, it means for x, I plug in a. So I'm going to have 3 times a minus 7. Now we're done. Can't do anything more, right? So general rule, if you plug in a number, you're going to output a number. If you plug in a variable, you're going to output something with a variable in it. Can't do anything more. What about if we plug in x plus h? This is a common thing in calculus, and we did this at the very beginning of the year. And this has to do with our definition of a derivative. So if we're plugging in x plus h, it's more than one term, right? It's a binomial. So I'm going to plug in x plus h in for x. Now, because I'm plugging in x plus h, I need those parentheses around it. So when we plug in x plus h for x, it's going to look like this. Same idea, just plug it in for x. But we can do a little bit more with that, right? We can distribute the 3. So when we distribute the 3, that's what we'll have. Now we're done. No like terms, nothing can be combined, simplified, la-da-da. So that's just a brief review, kind of an algebra review of functions. I'm going to do one more function when x is squared, so we can see what that one's going to look like next. Okay. So instead of making f of x linear, let's instead make it quadratic. So let's make it x squared plus 3. All right, so that is a quadratic function, right? It's a parabola. It looks something like this. So just general shape, right? Again, knowing what these look like is helpful for calculus. So linear functions form lines, quadratic functions form parabolas. And that plus 3 just means that those are our axes. Oops, I did that wrong, sorry. Those are our axes. This is up at 3, right? The coordinate point 0, 3 is on there. Okay, that's all that means. Let's plug in a couple things for it. Let's plug in 2. Let's plug in -1. And let's plug in x plus h. So when we plug in 2, right? We'll have 2 squared, 4, plus 3. So the coordinate point 2, 7 is on that parabola somewhere. 2, 7's on there. And then if we plug in -1, right, we'll square it. We'll get 1 plus 3. So we'll get 4. So the coordinate point -1, 4 is also on there. Okay. Now plugging in another function, right? Plugging in x plus h, or not a function, rather, a binomial, some variables. When we plug in x plus h, I have to plug that in for x. So I'm going to plug in x plus h, quantity squared, then plus 3. So I'm doing the same exact thing, but now I'm squaring it. Now don't you dare put x squared plus h squared. That is not right. We need to square the binomial. It means x plus h times itself. So I will write that all out. This means x plus h squared, then a plus 3. When we FOIL or multiply it out, we'll have x times x. We'll have x times h. We'll have, then we'll distribute our h through, so we'll have h times x, right, and h times h. So we'll have an hx plus an h squared. Okay, once we have that multiplied out, we can combine like terms. These middle 2 terms are like. They look different, but they're the same because multiplication is commutative. So xh is the same as hx. So we have an xh and another xh. So we have 2 xh's. We also had an x squared, and we had an h squared plus 3. So we're just plugging in x plus h, which we will see why on the next slide, why x plus h is important. So that is the pre-calculus knowledge that we need. This pre-calculus knowledge can be called like evaluating functions. Evaluate just means to like solve in a general way, kind of. So we're evaluating like f of 2, f of x plus h, and simplifying as far as we can go. This is as far as we can go because there's no more like terms or anything to distribute. Okay. Cool. All right, let's get into what a derivative is on the next slide, and I'm going to do that visually first. All right, so let's sketch just, let's actually sketch that function there. We'll sketch a parabola here. So there's my axes. Oh my. There we go. And before we get into this visual, I want us to realize that a derivative just means slope. Derivative just means slope. So let's graph a function. Let's graph a parabola. And let's call this y equals f of x. A nice little parabola there. Now, what I'm going to have you guys do is just not draw anything for these next couple minutes here. I just want you to watch the explanation for it because I'm going to like backtrack a couple times. I don't want you to have to erase or whatever. So let's think about a change, right? So a derivative is a change. It's a slope, right? We know that slope. You guys can unmute to answer. What's a way that we can define slope? Can anyone throw out what slope means, just algebraically?
Rise over run.
Rise over run, awesome. Any other definitions?
I like just like the M, like the one that's next to always.
Yeah,
Yeah,
it's M, right? It definitely is called little m.
Rate of change.
It's a rate of change, love it. why is it a rate of change? Like, why do we say rise over run? What is the maybe mathematical formula we could use for it? Does anyone remember?
Is that like y2 minus y1 over x2 minus x1?
You got it. So it's the change in how much vertical change we have, right? Change in literal y values, that's how much we're rising or falling, over running horizontally to the right. No, however this looks for you guys, I don't know, it's a mirror. But it's change in y, delta y, and a lot of you probably seen that delta before. I know I've done it, and maybe in physics. That just means change in. So it's how much we're rising or falling, change in y, divided by the change in x. Okay, so I'm just gonna throw out a couple numbers on this parabola, but then again, I'm going to erase them. So don't draw on your parabola right now. Let's just call this, it doesn't even matter what the function is. Let's call this A, and let's call this B. I wanna use variables so we don't think about this just in numerical terms. Let's think about it in a really like cool mathematical way. So then right here on the function, right, that coordinate point is A, f of A. That's what that coordinate point is. Its x value is A, and its y value is whatever we get when we plug in A to the function. So this coordinate point in a very general way is x comma y, A comma f of A. This coordinate point here, when x is B, would be B comma f of B. Now, what if we wanted to find the change that occurred on this function, or the slope between those 2 points? Now, in Algebra 1 and 2, you guys found slope of lines, right? It was literally rise over run, how much you changed. And you could count the squares on your graph if you wanted to. But in this case, I can't really find a linear change. This is curved. This is not a line. So if we want to find the change between A and B, we can make it a line. That is the best line I'm going to be able to draw with this. So that is the line between those 2 points. Let's find the slope of that line. So this is going to be the change, the rate of change from A to B. All right, the way we find slope, you guys told me already. It's down here. I'm going to use this definition right here because it's the most mathematical one. The y minus y over x minus x. Change in y, change in x. We want to go from the right point, left point. So our change, our slope, the y value here is f of b. The y value here is f of a. The x coordinates are b and a. Now I just used the second coordinate point first and the, because it's y2 minus y1, x2 minus x1. We could have very well written this in the opposite way and had f of a minus f of b over a minus b, but it's just better to go with your second coordinate first. Okay, so that is a more mathematical way. It's more abstract, right? We're not actually getting a value because I haven't given you any like function values here. This is just a general way to find the change between those 2 points. This is a pre-calculus way of finding change. We want in calculus to find what's called an instantaneous rate of change. How we're changing at an instant. How we're changing exactly at point A or exactly at point B or exactly at point X, wherever we are. So I'm going to redraw this on a different slide. Unless I can go back. No. We'll just redraw it. The idea is that I want A and B to get so close that instead of finding the rate of change over a time period between A and B, I want to find an instantaneous rate of change, the derivative. So let's take a look at that on a different slide. And this is where the H is going to come into play. So we'll have our quadratic again, our parabola. And instead of A and B, I'm going to generically just use X. Make it a little bit wider so it's easier to draw. Okay. Okay, so if we have the coordinate point X, f of X. So this coordinate point right here, its X coordinate is X, and its Y coordinate would be its output, which is f of X. Now my goal, instead of finding the line between 2 points on my graph, I want to find that line, how I'm changing exactly at X. Exactly at X. So I only want to go a little bit to the right, just a little bit to the right, so I can make that line almost perfectly on my parabola. If you notice, the line between here is basically on that parabola right there. But my goal is to get so close, to get to a point closer and closer and closer, so that when I draw that line tangent to my graph, it shows the exact change at that value. So I want it so close. I basically want to be adding almost nothing to X. I want to find the exact change at exactly that point. Well, how can we do that? We can get very, very close. I'm going to go back a little bit here. Oops, sorry. Okay. There we go. Okay, I want this other point to be close. All right, so I'm going to call this little distance in here between X and this other point, I'm going to call that little distance H. Then this point here is X plus that extra distance H. That distance is called X plus H. That's what that distance is. From the y-axis out to that point. That's that length right there, X plus H. So this coordinate point, this green coordinate point, is going to be X plus H, and its output is going to be f of X plus H. That's where that f of X plus H comes from. Now our goal, if you look at this line that's formed between these two, it still does not represent the rate of change that's happening at exactly X. It's capturing a rate of change of a smaller and smaller distance as this green point gets closer and closer to the red point, but it's still not capturing that exact distance. I can't capture the exact rate of change that's happening at X yet. I want this H, this distance between these 2 points, I want it to approach 0. But until we can do that, let's just write what the slope would be between these 2 points using our slope formula. Okay, so what would the slope be between those 2 points? What's our y2 value? Anyone see what y2 is?
F of X.
F of X plus H, good. Awesome. Minus, what's y sub 1?
F of x.
F of x. Cool. So we just did y minus y. Let's do x minus x now. Okay, what's our x2? What's our second x coordinate here?
X plus h.
X plus h. Minus, what's our first x coordinate?
X.
Just x. Good, so that's our second x coordinate, our first x coordinate. Great. So when we simplify in the denominator, we're left with the same numerator, so can't do anything there. But what's our denominator turn to? It turns to just h. X minus x cancels out. Now, the goal of this is to find what's happening not over a time period. There's some time lapsing in between here, or some distance lapsing. A lot of times it's time in calculus, like the x-axis represents like seconds or minutes, so that's why I'm using time. But it is technically a distance down here. We want that distance to basically be nothing. I want to find, how is this changing at exactly x? How are we changing exactly at x? So I basically want h to become nothing. But I can't do that because then I only have one coordinate point, and I can't find a slope with just one point. I need 2 points. So this is called the instantaneous rate of change, and we have to use calculus for it. We basically want this green point to get closer and closer to the red one, so that when we're finding it, we basically have 0 distance between them. I want this distance h to go to 0. That's called a limit. So in order to find how we're changing at exactly x, the derivative, which is the instantaneous rate of change, how we're changing at exactly 1 point. Instantaneous. We're going to use this idea of the rate of change between 2 points, which is just slope. And then we're going to define it as the limit as x goes to h. I'm sorry guys. I just got so flustered, I just got a phone call and had to like ignore it. Hang on. We wanted h to go to 0, right? That's what we were talking about. So we want the limit as h goes to 0 of this, of f of x plus h minus f of x all over h. This is the definition of our derivative here. So again, we have to use the idea that derivative is slope, okay? Average rate of change between 2 points. Calculus wants us to find the rate of change at an instant, at 1 point only. Well, that's kind of difficult because in order to find slope, we need 2 points, right? Y minus y over x minus x. Well, we can use the idea of those 2 points getting so close to each other that their distance between them goes to 0, and we're still finding the slope between those 2 points, as their distance is basically nothing between them. So that really allows us to find the change at that exact instant. The way that we can also define this is called f prime of x. Now, I know this is a lot. It's a lot. But this is the way that we define the derivative of a function. The derivative is the instantaneous rate of change, and it's defined as f prime of x. F prime of x. So let's do an example to find that derivative. And I'll rewrite this on the other screen here. Okay, our definition of a derivative is as follows. So we are going to be using that f prime of x, the derivative, is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's what we determined on the page before is what it is. Okay, let's use that for this function here. Let's say f was our first function that we came up with on the first page, which was 3x minus 7. Okay, 3x minus 7 is a line. What's the slope of that line?
It's 3.
It's 3. Does that line ever change slope? Is it like curvy? A line's just straight always, right? So the slope of that line's always 3. Therefore, its derivative anywhere is 3. Derivative is just how we're changing, our slope, our rate of change. We are going to get 3 out at the end by doing all of this fun stuff. And I'm going to show you that we'll just get 3. Derivative is glorified slope. So for a line, slope's always 3 everywhere. That's what makes it a line. It has a constant rate of change of 3. All right, so let's use this limit definition of a derivative for this function. All right, so to find f prime, it's going to be defined as the limit as h goes to 0. Then I have to plug in. I first have to find f of x plus h. Well, how do we do that? We have to plug in x plus h into this function. So I'm going to plug in x plus h here first. So we're going to have 3 times x plus h minus 7. That's the first part. I just did this part. Minus f of x. Well, what's f of x? F of x is 3x minus 7. It's plugging in x to the function. We're going to do minus f of x. Now, because we're subtracting something that has more than a term, we need to put it in parentheses. All over h. So I'll go through this one more time. So I first plugged in x plus h to get this part of our limit definition. That means we had to plug in x plus h to here. So we did. So this is f of x plus h right here. Then we subtracted f of x. F of x is 3x minus 7. I put it in parentheses because we're subtracting something with more than one term. All over h. All right, so let's simplify that a little bit. So it's going to be the limit as h goes to 0. Then we can distribute our 3 through. So when we distribute the 3, we'll have 3x plus 3h minus 7. Then when we distribute our negative sign through, right, we'll have minus 3x plus 7. All over h. Then we can clean up the numerator a little bit. So we'll have the limit as h goes to 0. When we clean up our numerator, 3x minus 3x cancels. Negative 7 plus 7 cancels. So we're left with 3h only in the numerator. And of course, we're left with h in the denominator. Now, what can we do top to bottom here?
Cancel the h's.
We can cancel the h's, exactly. Now, if you look at your limit from the get, right, we determined that to like evaluate a limit, we use direct substitution. We did that right before break. If you were to plug 0 in for h, I don't care what you get up here, I'm dividing by 0. No good, right? So we saw that, hey, some stuff canceled in the numerator. So look what we're left with. But then if we still plug in 0 for h, we're left with 0 over 0. That's called indeterminate form, something we learned a few weeks ago. So we factored. Well, we can't factor anything, but algebraically, we can just cancel the h's out. We're left with 3. Technically, we're left with the limit as h goes to 0 of 3. Well, there's no more h's to plug in. This is just the 3. So no matter what we plug in for h, it doesn't matter. Our answer is 3, which is what we knew we were going to get from the jump. Remember, derivative, f prime, is just glorified slope at any point. This is a line. Its slope everywhere is 3. That's the m value. So we determined it using calculus that it's 3. Okay, let's do one more that's a little bit more challenging, that has a squared in it. Okay, same directions. I'm not going to rewrite them, but I will rewrite this. This is the limit definition of a derivative. And we'll color code it. Okay, let's say our function is, I think the other one we had was x squared plus 3 in the beginning. So we'll use that. All right, so let's find f prime using our definition for what it is, the instantaneous rate of change, the definition of the derivative. So f prime is defined as the limit as h goes to 0. So we're just plugging in. That's all we're doing, is we're plugging and chugging. Okay, the first thing that we need to find is f of x plus h, what's in green. That means we need to plug in x plus h here, which is x plus h squared plus 3 minus, we need to subtract f of x. Well, what is f of x? It means plug in x everywhere. Well, it already is. It's x squared plus 3. That's literally what f of x equals. So we're subtracting x squared plus 3. Again, in math, when you subtract, put it in parentheses. All over h. Now, on the other page, we found out what happened when you squared x plus h, right? It means x plus h times x plus h. And what we got out was x squared plus 2xh plus h squared. That was what we got out when we did x plus h times x plus h earlier. We got this. Could always multiply it out to the side if you need to see it again. Then, of course, we have the plus 3 after it. Then we're going to subtract both of these terms in here by distributing the minus sign. So we'll have minus x squared minus 3 all over h. Again, I can't just direct substitute 0 in for h right now. I got issues with it. No good. Can't plug in 0 in the denominator there. So let's clean up the numerator. The rule of thumb is that everything that doesn't have an h in it should go away. So we have the limit as h goes to 0. And then when we simplify, this doesn't have an h in it, x squared. It cancels with a minus x squared over here. These are gone. This does have an h in it, so does this term. Those are not going to cancel out with anything. All that is left without an h is a plus 3 and a minus 3. Those cancel out. They done. So we are left with 2xh plus h squared all over h. That is what we are left with, everything with h in it. Now we can't just cancel yet. It's not just one term over another term that makes it easy to cancel. we learned that if we still get 0 over 0, which we will if we plug in 0 for h, we have to factor. How can we factor the numerator?
Factor out an H.
GCF, you got it. Let's factor out the h in the numerator. So it's going to be the limit as h goes to 0. We'll factor out an h up top. Therefore, we're left with 2x. And then here we're left with a plus h over h. Because we've factored, we can now cancel this h and this h. We cannot cancel this h in here because it is part of a plus or minus with another term. It does not cancel with this solo h down here. So basically now we can plug in 0 for h. We can direct substitute now because it's no longer 0 over 0. We're rid of that. So we can plug in 0 for h now. If we plug in 0 for h, this term becomes 0 here. Okay, so then when we plug in 0 for h, we're left with just 2x because we plugged in 0 for h. And that is what f prime is. This original function is a parabola. The original function looks like this. It does not have a constant rate of change like a line. Its rate of change is constantly changing. If I wanted to figure out what the rate of change was here, it's negative. Our function's going down there. But the rate of change at this point, how are we changing there? It's positive. So the rate of change changes all the time because it's no longer a linear function, it's more complicated. So our instantaneous rate of change is determined by where we're looking at it, what the x value is. That is where I'm going to end for you guys today. I know that was a lot. I'm going to send out your assignment today, but most likely you will want to work on it after class Wednesday when we do a few more examples. If you'd like to get it done earlier, join me for office hours today at 2. We can do some examples, but we're going to continue with way more examples on Wednesday for you guys. But I already sent out your assignment this morning. It's not going to be due till, I think, end of day Thursday. Guys have any questions for me? All right, you got this. You got this.
Oh, I have one question.
Sure, what's up?
I'm missing an assignment. What is that? It's the 4-9.
Okay, why don't you join me at